All right, so today's lab is on Ohm's law and parallel and series circuits. Let me pull up Canvas and I'll share my screen. Go here and like that. Okay, you can follow along on your own uh, Canvas. In the assignments, we have our instructions like normal. And this is it's a bit bigger of a lab assignment. There's a lot more individual things to do for you to measure. So be aware of that it's worth 60 points. And I have to change that. It's not due Friday, it's due Sunday. So I'll edit that, it says Friday. It's due at our normal time on Sunday, right here. Okay, so we have our instructions. Go into the instructions. It's same sort of formats. You could fill out just like normal. And in this particular lab, we're going to this PhET simulation website. Once you click on the link, it's going to take us to something that looks like this. In here, we click on intro. That's where we're going to be doing all of our experiments for today. Click on intro, and we have a array of circuit elements on the left, and we have some tools on the right. Wire, battery, resistor. We're going to be using a handful of these for today's lab. Let's go into the instructions. So starting out, we have, we're going to make a very simple circuit of one battery and one resistor. The physical representations on the left and the circuit diagram is on the right. You're going to go in and, test out measuring with these, with this very simple circuit. Let's go back into it. So let me just very simply, I'm not going to do the measuring that you have to do. That's a wire. We need a resistor and a battery. And you can think of these as floating out in space. And we don't have a complete circuit until we make a complete loop. So let's get this wire out here. And you connect the dotted ends. And you're basically connecting a wire from one end of one element to one end of another element. You can see there's no flow of charge. This isn't a closed loop yet. So this isn't a circuit quite yet. We need to close the loop. So we add one over here and close the loop. You can see there's this flow of charge now. Okay. In the instructions, we're going to be measuring throughout the lab. We're going to be measuring voltages, and we're going to be measuring the current, so amps. So thing to keep in mind for that is we have on the right, those are our tools. We have a voltmeter and we have an ammeter. So measures voltage, this measures current. Thing about a voltmeter is you can't just place one of these probes. You can move these around. You can't just place one of them on one thing by itself. You see there's no value on the screen right here. To measure voltages in real life, you have to go across the object you want to measure. So you measure on one side of the thing you want to measure, then you have to go on the other side. So for this example, let's just do the battery. I'll put one end on this side of the battery, and I'll put the other end on the other side. So voltages, you have to measure across something. Okay. It doesn't matter particularly which side is on which. So if I had it like this, that's -9. If I switch them, it's just going to switch the sign, +9. That's not too critical for today's lab, the sign of the value. When you're measuring current, it only has a single probe. So you place this wherever on the circuit it tells you to. Okay. All right, let me go back to the instructions. We have this very simple circuit. This is sort of the first one that we are taught. This is the first one we experiment with. We're going to quickly go into something that's a lot more complex. Let me scroll down. Here, we're going to have a series circuit with 2 light bulbs in the circuit. And it's a series because the charge may flow out of one end of the battery. It has to go through one element, and then it's forced to go through another element, and it returns back to the battery. So that's a series. It's a simple series. There's only 2 elements in it. We're going to measure some specific quantities. We're going to measure voltages. Your uh, setup won't have these labels on it, so you won't have like bulb 1, J2, J3. Those are just there to help you visualize where you have to measure on the screen. Okay, so that's just the measuring part. There's going to be a lot of subtle changes and then measuring how the circuit has changed. So similar thing, measuring here. The next part is measuring or setting up a parallel circuit. This is something also has 2 light bulbs, but they are arranged in a parallel fashion. Same sort of thing, measuring voltages and measuring the current. Okay. This is going to be a large part of a lab, is just trying to visualize and rearrange these best you can. At the very end, we're going to analyze our data. It says right here, measuring voltages and current. We're going to be doing that for all of these. At the very end, we need to analyze the data. So what is something common that we've seen in all of our voltages or in all of our voltage measurements? How do they act? So let me go down specifically. So in this summary section, so if you look right here, it's not necessarily asking you a question, it just wants you to check. This is where you state any relationship that you see. You check to see if your own data matches what it should actually happen. Same thing for 4.2. At the very bottom, write a short paragraph describing your own measurements, support these statements. It's a similar thing. I'd say if you make this very thorough, that can count as your conclusion for today. So recap the lab, recap relationships that you see, and that'll be good. At the very end, instead of typing out your sort of feedback for the lab, if you could go to this form, and it's not graded, it's just your own opinion on how the instructions are laid out. If anything could be clearer, this is for the lab coordinator. It's a bit more direct. He gets them more direct this way. So if you could fill those out, that would be great when you finish. Okay. So there's a lot of small individual things to measure, let alone setting it up correctly. I would advise everyone to stay and work on it, especially for these parallel versions down here. But I'm only requiring, or I'm only checking off for today, that you do this first one. So task 2.1, simple series circuit. So with the 2 light bulbs, I just want to see this first set of measurements and just checking to see if you know where you're measuring, you know how to use the tools correctly. You know, I'm just checking this data. After that, I'd say you are good to go, although I'd encourage you to stay and work on the rest. Okay, so that's sort of my expectation for today's lab. Are there any questions before I get to some notes? If there are, go ahead, shout them out. I'm going to switch screens. Get this. Okay. All right. So today is Ohm's law. With series and parallel circuits. Okay. Let's start. This is going to be very basic starting points. Just in case anyone hasn't gotten to circuits yet in lecture. We have the symbol of a battery. The circuit diagram symbol for a battery is this. It has, you can imagine this is sort of like a large metal plate, and this is a small metal plate right here. And it has these 2 wires coming off of the ends. This is a battery. Okay. The next symbol is a resistor. Doesn't necessarily matter how many zigzags there are, but it's sort of this, zigzag uh, drawing right here, and again, 2 little end wires coming off. So that's a resistor. Now, we can't just have these things floating out in space. This is, just like this. This is a battery that's not connected to anything. It's sitting on my desk. Same thing with this resistor. Okay. Let me get this actually real quick. Okay. So we need to connect these 2 things together. Just like our lab today, I'm going to put this sort of dotted circle around each end. This isn't typically here in a real diagram. I'm just going to make something a bit clearer. So I'm connecting the ends together by using just any wire that I find. So I'm going to add my own wire right here. And the ends would connect. I'm just having a demonstration right now. Okay. All right. But let's go like this. So this large plate is typically the positive side of the battery. On a a double A battery, there's sort of that pointed end. That's always the positive side. As I said earlier, there is no real flow in this circuit yet because it's not a closed loop. We need to close this loop. The charge will come out of the positive end, go down the wire, go turn the corner and go through the resistor, but it doesn't want to do that because there's nowhere for it to go over here. It doesn't know what to do, so it's not going to flow. In order for it to flow, I need to have that closed loop like this. So I add another wire and it returns back to the battery. So it will flow out, around, down the wire, through the resistor, and return back to the battery. Now, why is there some kind of flow now? Why does it want to return back to itself? That's a big question. Let me put this positive a little smaller right here. I'll erase that. Okay, so you could think of this large plate on the symbol as, a large metal plate that's holding a lot of individual, go like this, holding a lot of individual charges on it. So they're held on the plate. You think of the small plate having none on it. You might see a battery in the store. It's rated 9 volts. That means, we learned 2 weeks ago about voltage. Voltage is a difference. There's a potential difference. So a battery that's rated at 9 volts actually means there's a potential difference between this plate and this plate of 9 volts. More specifically, I could go like this. More specifically, there is a potential, electric potential on this large plate of 9 volts, and there's a electric potential of 0 volts on the small plate. And there's this difference of 9. That's why batteries are just rated with a single number, 9 volts. Okay. Since there are a bunch sort of together, they don't like being close to each other. They want to escape. And it's not until the loop is connected where they see that the charges will tell that there's this opening down at the other end of the battery that encourages them to flow through the circuit. That way they can return to this space with 0 volts. If you want to think of the water and the tube example, this 9 volts plate, this larger plate, that is like high pressure region, and the 0 volts, that's the low pressure. And water always wants to flow to a lower pressure. Same thing with these charges. Okay, so a lot of arrows on the screen. I will rid of these. Actually, no, that's fine. I'll make a cleaner one down here. Okay, that's the battery. And let's talk about this resistor. Resistance from last week we saw was just R. Typically in a circuit, resistors kind of all look the same. Let me bring this over. So here are resistors in a circuit. They kind of all look the same. There are these small little things. This is the resistor. These are the wires coming off of it. But since they're all the same size, we learned last week that the cross-sectional area affects resistance, the length affects the resistance, The only other thing that we can think of how they're different is the material inside of them. So each of these has slightly different materials inside of them. And if you look at a circuit, there's color coordination that tells you actual values on the resistor. So we don't have to actually measure them or write tiny little numbers on each one. So those are the resistors, and they're different because of the material in them. Let's go to how voltage and resistance can be used to find the currents that flows through each element. So let me just jump to writing the equation, Ohm's law equation, which is V equals I R. This is voltage. Voltage. This is current. And R is resistance. Okay. Units of voltage should be familiar. It's just V. The units for resistance we saw last week was ohms, capital Omega. The unit for current is amperes, or we just call them amps. The symbol is A, capital A. Okay. When we think about what's different between voltage and currents, that's when we kind of have to stop thinking of it as water flowing through tubes. It's a bit difficult to perceive how these two things are different from one another. So we'll leave that for thinking about just charges flowing through a circuit. Let's go into talking about some circuits. So let's on the left, let's make a series circuit. Series on the right, we'll make a parallel circuit. Okay, and I want to, I had this I had this simple one up at the top. Let's make it just a bit more complicated for these two. This is something similar to today's lab. So say I want a battery, and we're going to put it sideways like this. And I want to connect this battery to two resistors in a series. So series means one right after the other. So it's one big closed loop. So let's go like this. I have to add a wire. I'm just making this a big sort of wire so I can clearly see what's happening. And it's going to go through one resistor. And then it will go through another resistor. And the charge will have to return to have a closed circuit or a closed loop. Let's do this. We'll call this one R1. That's the first resistor. And we'll call this one R2. That's the second resistor. Something to the battery, typically just V. Something to keep in mind, or something that you should be observant about, or let me have this sort of in bold at the top. I'll put that. Circuits have to have closed loops. Okay. All right. So we have this series circuit on the left. It's one big closed loop. I'm just going to put this sort of looping symbol right here. Okay, that's one big closed loop. It gets complicated, or a bit more complicated, when we talk about parallel circuits. Let me do the same sort of starting point. So a battery that's on its side like this. And I should have noted there's the positive sides on the top. Okay. And let's put two resistors in parallel with one another. So I'm gonna add a wire, and I need to have one resistor. I'll add it right here. And I will have it return back to the battery. Now, something that's in parallel, that means that there's a choice given to the charge flowing in the wire. So I'm going to add these dots right here. These are called junctions. This would also be a definition sort of term. So a junction, I don't want to write too small right here. So the charge will come out, flow around, and as soon as it gets to the junction, let me finish this drawing first. That's where we have our crossroads and our choice given to the charge. So at the junction, the charge then has to choose which path to take. Is it going to go through resistor 1, or is it going to go through resistor 2? How is this going to, change any of the values that we measure? That's something that we're going to investigate today. So it's going to get to this junction, and let's say it does go through, it does turn and go through resistor 1. In fact, let me put, this is a bit small picture. So let's say it does go through resistor 1, and it's resistor 1 right there. Okay. Goes through. Once it gets to this junction down here, it will return back to the battery. Now we have to see that this is a small closed loop. If you look at this sort of, small path right here, the battery, and there's only one resistor in this small loop. Let's look at if the charge took the other path. So gets to the junction and it chooses to go this way. Turn the corner, it would go through resistor 2, turn the corner again, and once it's at this junction, it's going to choose to go to the battery because that's where it wants to go anyway. Now we need to look at this sort of second choice as a large loop. So on the outside, look at the outside line. That's one big loop. I'm just adding way too many arrows. So you can see there are separate loops, separate closed loops in a parallel circuit. Something that's, let me put this right here. Do that. Something that I think you might be at in lecture this might be helpful. I think I can put this in these notes since I'm already here, is how do we use Ohm's law with these two types of circuits? So there's V right here. So how would I use V equals IR when there's two resistors? What do I have to do? Which one do I choose? Well, it's difficult to do that at this specific point if we don't know um, the current. So we would have to sort of take these two resistors and lump them together in one bit as one big resistor. Let me do that. I'm going to call this, I'm lumping these two together. So I'm sort of ignoring that they're two, and I'm saying that's just one big one. That's going to be called R total. So the total resistance. So for resistors in series, the resistance acts like this. Total R1 plus R2. Now, these rules that I'm writing down right now aren't going to be in the lab. I'm already here. I think I could at least write them down. They may be in future labs. You're definitely going to see these in lecture, or maybe have just seen them. So what I've done is I've lumped these two resistors together, so now I can simplify the circuit so it looks like this. So instead of 1 and 2 separately, I've lumped them together. Now I could call that R total. And if I know the initial voltage and I know R total, that's how I can find current. And then move on from there. How do I do that? How do I find current or any other thing using Ohm's law with a parallel circuit? It's a similar process. I need to lump the resistors together. I need to lump the elements together as one big one. So this picture is very messy. The notes will be a little clearer when I put them up later. So lumping these two together. However, resistors in parallel act a bit differently. So in order to differentiate, I'm just going to call this one R equivalent instead of R total, just so we know it's different. Oh, write that smaller. Okay, down here I'll just put R. Oh. The equation for this is not as direct. We need to do this. 1 over R equivalent EQ equals 1 over R1 plus 1 over R2. All right, so resistors in parallel act a bit differently. That's how we need to handle those. Okay, again, you're not going to need these for today's lab. I just thought they would fit well with the notes I'm already going over. So we have simplified this end of this circuit. So now we see a simplified version that looks like this. Once we, add them, flip the fraction, we'll have our equivalent right here. And that's how we can find, currents and whatnot. That will be helpful later. The final thing that we're going to have, we're going to cover next week, it's going to be over the same topic, is Kirchhoff's laws or Kirchhoff's rules. Let me just at this point sort of point out to everyone, be aware of where the closed loops are and be aware of where junctions are. And something to keep in mind while doing today's lab, I'm just going to have this as a question, is what are, I think there's two H's and two F's. So laws or rules, let me put rules. So that's something you can look up, and it might be helpful for today's lab. Why I'm having you just look them up, because I think next week's lab is going to be entirely on it, so I don't want to get there quite yet. Okay. Are there any questions with the notes? Okay. All right. Let me do this. Let me get the rooms up. Oh. Yeah. So I really only want to see those first measurements, and after that, you can stick around if you want, or you're good to go.